Now in part B, we have a different error. So read the burette to 2 decimal places. We've taken care of part A. Let's take a look at part B. I wrote down 37.79 for my volume reading, but the student wrote down 38.21. So another common mistake that can be made by AP Chemistry students is to read the burette incorrectly. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 4.5 and 4.6. As you can see on this slide, these topics fall under Unit 4 in the AP Chemistry curriculum, Chemical Reactions. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for Topic 4.5, Stoichiometry. Here are some essential knowledge statements from the AP Chemistry course and exam description. Because atoms must be conserved during a chemical process, it is possible to calculate product amounts by using known reactant amounts, or to calculate reactant amounts given known product amounts. Coefficients of balanced chemical equations contain information regarding the proportionality of the amounts of substances involved in the reaction. These values can be used in chemical calculations involving the mole concept. Stoichiometric calculations can be combined with the ideal gas law and calculations involving molarity to quantitatively study gases and solutions. Now let's move on to the practice for Topic 4.5. This is question 1. In question 1, we are given a balanced chemical equation, and it says, in a certain experiment, a sample of liquid C2H3Cl reacts completely with oxygen gas in a chemical reaction according to the equation shown above. Calculate the mass of oxygen gas that is required to react completely with 16.75 grams of liquid C2H3Cl. So the first thing I'm going to do to kind of plan my strategy is I know that I will need the molar mass of these two substances, these two reactants. So the molar mass of C2H3Cl is calculated from the periodic table. So I have 2 carbons, 3 hydrogens, and 1 chlorine. So that molar mass is 62.494 grams per mole. And then for oxygen gas, that would be 2 times 16, or 32 grams per mole. So my general strategy will be to use the molar mass of C2H3Cl to convert the quantity that I was given, 16.75 grams, into moles. Then I will use the coefficients in the balanced chemical equation to convert from moles of one chemical to moles of another. And then finally, I will use the molar mass of the other substance to convert from moles into grams. So it's going to be a 3-step process where I go from grams of one chemical to grams of another. So let's begin with 16.75 grams of C2H3Cl. My first conversion factor involves the molar mass. So that's 1 mole of C2H3Cl over 62.494 grams of that chemical. Now, is it going to be 2 over 5 or 5 over 2? This is why it's important to write the units. So I'm going to put moles of C2H3Cl on the bottom and moles of O2 on the top. So it's going to be 5 over 2. So 5 moles of O2 for every 2 moles of C2H3Cl. And then finally, I'll use the molar mass of oxygen, so 32 grams of O2 over 1 mole. So now I'm all set up. I'll pick up my calculator, 16.75 divided by 62.494 times 5 divided by 2, and then times 32. So here's my unrounded answer. So now I'm going to round that off to the appropriate number of significant figures. Since the number that I started with was 16.75, and that has 4 significant figures, I will round off my final answer to 4 significant figures, so 21.44 grams of oxygen gas. All right, well, that's the answer to question 1. Now let's take a look at question 2, which is a multiple choice question. In question 2, it says, which of the following will produce the greatest mass of carbon dioxide gas when it undergoes complete combustion with oxygen gas? Now, in this question, it refers to a combustion reaction with oxygen gas. However, we are not given any balanced chemical equations. So a good first step might be to write some balanced equations for these combustion reactions. So a combustion reaction with these 4 substances involves a reaction with O2, and then the products of the chemical reaction are both carbon dioxide and water. So in the first example, we have CH4. If that reacts with O2, I produce carbon dioxide and water. Now, the carbon atoms are already balanced. I see 4 hydrogen atoms on the left, so I'll put a 2 in front of the H2O. I see a total of 4 oxygen atoms on the right, so I will put a 2 in front of the O2. Now, our next chemical formula is C2H6, again, reacting with oxygen to produce carbon dioxide and water. I see 2 carbon atoms on the left, so I will put a 2 in front of the CO2 on the right to balance the carbon atoms. I see 6 hydrogen atoms on the left, so I will put a 3 in front of the water on the right to balance the hydrogen atoms. Now there's a total of 7 oxygen atoms on the right, and I'm okay for right now putting a fractional coefficient in place to balance the oxygen atoms. So to get 7 oxygen atoms on the left, I will put 3.5 or 7/2. Now the next chemical formula is C3H8O. That would be 3 carbon atoms on the left, so I'll put a 3 in front of the CO2 on the right. I see 8 hydrogen atoms on the left, so I'll put a 4 in front of the H2O on the right. And there's a total of 10 oxygen atoms on the right. So with that single oxygen atom in the first chemical formula, I need 9 oxygen atoms to come from the O2, which means, again, another fractional coefficient, so 4.5 or 9/2. So now that equation is balanced, and let's move on to our last chemical formula, which is C4H8O2, again, reacting with oxygen to produce carbon dioxide and water. I see 4 carbon atoms on the left, so I will put a 4 in front of the CO2. I see 8 hydrogen atoms on the left, so I will put a 4 in front of the H2O. And on the right side of the equation, I see a total of 12 oxygen atoms. Now, there's already 2 oxygen atoms in that first chemical formula, so I need 10 oxygen atoms to come from the O2, so I can put a 5 in front of the O2. Now, at this point, you might think this is going to be a long, complicated process, but I'm going to simplify the strategy. What we need to do is focus our attention on where does this carbon dioxide come from. So in all 4 of these chemical reactions, the carbon dioxide comes from the atoms of carbon on the left side of the equation. So the carbon atoms in each of these 4 samples are converted into carbon dioxide. This changes the strategy for how we answer question 2, because the sample that contains the greatest number of carbon atoms will produce the greatest amount of CO2. So we now have a strategy for answering question 2. So our strategy for answering question number 2 is now focused on answering the following question. Which of these samples contains the greatest amount of carbon atoms? So I'm not looking at those balanced equations anymore. I'm just focusing on converting grams of each substance into moles of carbon atoms. This will be a 2-step conversion. So I'll start with choice A. I have 65 grams of CH4. First, I'm going to convert from grams to moles using the periodic table. So here is my calculation for the molar mass of CH4. So I'm converting from grams to moles. So times 1 mole of CH4 over 16.042 grams of CH4. And now I'm going to convert to moles of carbon atoms. And so because carbon does not have a subscript in the chemical formula CH4, that would be 1 mole of carbon for every 1 mole of CH4. So 65 divided by 16.042, that gives me a value of 4.05 moles of carbon, and I will write that quantity next to choice A. Now, moving on to choice B, it's going to be the same process. So 75 grams of C2H6. First, I will convert from grams into moles, and you can see I'm showing my calculated value for the molar mass of that substance. So times 1 mole of C2H6 over 30.068 grams. And now because there is a subscript of 2 next to the carbon in that formula, there are 2 moles of carbon for every 1 mole of C2H6. So 75 divided by 30.068 times 2, and that gives me 4.99 moles of carbon atoms. Now, since I'm looking for the sample that contains the greatest amount of carbon atoms, now I can eliminate choice A because 4.99 is greater than 4.05. Moving on to choice C, same process, grams to moles. So 85 grams of C3H8O. There's my calculated value for the molar mass of that substance. So 85 grams of C3H8O times 1 mole over 60.094 grams. Now I see a subscript of 3 for the carbon. So there's 3 moles of carbon for every 1 mole of this substance. 85 divided by 60.094 times 3 gives me a value of 4.24 moles of carbon. And again, since that question is looking for the greatest amount of carbon atoms, and choice C has 4.24 moles of carbon, which is less than 4.99 moles of carbon, I can eliminate choice C. Finally, choice D, 95 grams of C4H8O2. So I will first divide by the molar mass, so times 1 mole of C4H8O2 over 88.104 grams. I see a subscript of 4, so there's 4 moles of carbon for every 1 mole of C4H8O2. 95 divided by 88.104 times 4, and I get 4.31 moles of carbon, which again is less than 4.99 moles of carbon. So that makes choice B the correct answer. So you'll notice that I didn't need to convert all the way from grams of each substance into grams of CO2. Once I determined the substance that contains the greatest number of carbon atoms, then that substance will contain the greatest amount of CO2. Hopefully that strategy made sense to you. I was trying to be very efficient with how I solved that problem. So the correct answer to question 2 is choice B. Now let's take a look at question 3, which is a free response question. In question 3, we are given a balanced chemical equation, and it says, a chemical reaction between maleic acid and sodium bicarbonate occurs in the presence of water to produce carbon dioxide and sodium maleate as represented by the following equation. So again, we have a balanced chemical equation, and then I can see a data table. It says, a student combines samples of maleic acid and sodium bicarbonate with sufficient water and takes measurements to determine the mass of carbon dioxide gas produced. Data from the experiment is recorded in the following table. Assume that the reaction proceeds until one of the reactants is completely consumed in each trial. Now, we have 2 trials, but I'm going to focus my attention on trial 1. And the reason why I'd like to focus my attention on trial 1 is because of this first question in part A. So it says the student performs the following calculations based on the data from trial 1 of this experiment. So they took 1.543 grams of maleic acid and they converted from grams to moles. And then they took 1.251 grams of sodium bicarbonate and converted from grams to moles. So now they have two different numbers. They have moles of maleic acid and they have moles of sodium bicarbonate. So here comes the part A question. It says the student claims that the identity of the limiting reactant in trial 1 of this experiment is maleic acid, because the number of moles of maleic acid, so you can see 0.01329 versus 0.01489, they say that the number of moles of maleic acid is less than the number of moles of sodium bicarbonate. So do you agree or disagree with the student's claim? Justify your answer. So we are talking about limiting reactants in this question, and I will just show you this slide. This comes from my video for topic 4.5, stoichiometry. So there are two strategies to determine the identity of the limiting reactant. One strategy is you compare how much reactant is needed with how much reactant is available. So you would use stoichiometry calculations to convert the available amount of each reactant into the amount of the other reactant that is needed. Now, that is a good strategy, and it does involve the coefficients from the balanced chemical equation. Another strategy, which also works to determine the identity of the limiting reactant, is you use stoichiometry calculations to determine the theoretical yield of each, as in you convert the available amount of each reactant into the amount of product that could be produced from it. And what's important about this strategy is that the reactant that leads to the smaller amount of product is the limiting reactant. That's very important, that the reactant that leads to the smaller amount of product is the limiting reactant. Now let's go back and analyze how well did the student do their analysis to determine should we agree or disagree with the student's claim. So what did they do? They converted grams to moles. Did they use the coefficients from the balanced chemical equation in their analysis of the limiting reactant? And the answer is no. So the student did a good first step by converting from grams to moles. However, they need to keep going. The next step is to use the coefficients from the balanced chemical equation. So we are setting ourselves up for determining the theoretical yield by going from each reactant into product. So that's what I'm going to do. I'm going to take the student's first step, which is grams to moles, and now I'm going to consider the coefficients. I'd like to choose carbon dioxide as my product because carbon dioxide is being produced and that's listed in the data table. So let's take a look at the coefficients. So I'm highlighting the coefficients from the balanced chemical equation so I can do my next conversion factor. There are 2 moles of CO2 produced for every 1 mole of maleic acid. So the student did not include that in their calculation. When I do that math of 1.543 divided by 116.072 and then times 2, I get 0.2659 moles of CO2. Now I have to continue that process by starting with the other reactant. So I'll begin with the sodium bicarbonate. 1.251 grams of sodium bicarbonate. This is what the student did, converting from grams to moles, but now here comes the next part. What are my coefficients for carbon dioxide and sodium bicarbonate? So I'm highlighting them from the balanced chemical equation. There are 2 moles of CO2 produced for every 2 moles of sodium bicarbonate. Again, the student did not do that calculation. And when I do 1.251 divided by 84.008, and then of course times 2 over 2 is not going to change that, I get 0.01489 moles of CO2. So now that I've done a conversion of each reactant into product, here comes the question. Which of these two values for the number of moles of CO2 comes from the limiting reactant? So as I mentioned, it's important to realize that the limiting reactant is the one that produces the smaller amount of product. And so because we can see that 0.01489 moles of CO2 is less than 0.02659 moles of CO2, we have identified the limiting reactant as sodium bicarbonate. So why is sodium bicarbonate the limiting reactant? Because it leads to a smaller amount of product in your stoichiometry calculations. So we're going to set ourselves up to disagree with the student's claim. Now, a little transparency here. You're going to notice that this particular question actually comes from a released AP Chemistry question. So I'll show you which one. It was actually from the 2024 AP Chemistry exam. Now, this was question 2. You can see it says a chemical reaction between maleic acid and sodium bicarbonate occurs. I have slightly modified the information in that data table, and the original question, this is number 2, part C, from the 2024 AP Chemistry exam, it said, based on the student's data, identify the limiting reactant in this trial and then justify your answer. So now what you're looking at is the official scoring guidelines. So here's one strategy for determining that the limiting reactant was sodium bicarbonate. So if we look at the 2 different trials, we notice that the mass of maleic acid stays constant. The mass of the sodium bicarbonate increases, and look what happened to the amount of carbon dioxide produced. It also increases. So on the official scoring guidelines, one justification for identifying the sodium bicarbonate as the limiting reactant is this one. It says sodium bicarbonate is the limiting reactant because changing the mass of sodium bicarbonate alters the amount of carbon dioxide produced. So if you increase the amount of the excess reactant, it will have no effect on the amount of product produced. On the other hand, if you increase the amount of the limiting reactant, then this will increase the amount of product produced. Now, the other strategy for identifying that sodium bicarbonate is the limiting reactant is what I have already showed you in an earlier slide. And I'm converting each reactant into product. So you can see from these stoichiometry calculations that sodium bicarbonate is the limiting reactant because the amount present has a smaller theoretical yield of the carbon dioxide product. Now, one more thing I'd like to show you is what's called the Chief Reader Report, and it identifies common misconceptions that students make on the AP Chemistry exam in terms of their responses. So for this particular question, common misconceptions included the following. Some students only compared the mass of the reactants to justify their identity of the limiting reactant. Some students only compared the molar mass values. Some students only compared the coefficients. But as you can see, it says often an incorrect calculation only compared the calculated moles of sodium bicarbonate to the moles of maleic acid without referencing the stoichiometric ratio between the reactants. So that's why I chose to write this particular question to highlight that when you are identifying the limiting reactant, you should always use stoichiometric analysis involving the coefficients from the balanced chemical equation. So if you convert each of the reactants into product, the limiting reactant is the one that produces the smaller amount of product in your stoichiometry calculations. Now let's go back to part A of this question. So we are going to disagree with the student's claim that the identity of the limiting reactant is not maleic acid, but rather sodium bicarbonate. So this is what I said. I disagree with the student's claim. The student only compared the number of moles of maleic acid with the number of moles of sodium bicarbonate. What they also should have done is to use the coefficients from the balanced chemical equation. If they had calculated the amount of carbon dioxide that could be formed separately from each reactant, then they could have shown that the limiting reactant is actually sodium bicarbonate, because 1.251 grams of sodium bicarbonate leads to a smaller amount of CO2 in the stoichiometry calculations. So you can see that the limiting reactant is the reactant that leads to the smaller amount of product in your stoichiometry calculations. All right, now let's go ahead and take a look at part B of this question. In part B of this question, we have another data table. This is for trial 3, and it says, on the basis of the experimental data shown in the table above, determine each of the following for trial 3 of this experiment. You must show the setup for your calculations in addition to your final answer for each part of this question. So the first part is to determine the identity of the limiting reactant. I will use that same strategy that I already showed you, which is let's convert each reactant into product. And whichever reactant leads to a smaller amount of product in our stoichiometry calculations, that will be the limiting reactant. So I'll start with 2.135 grams of maleic acid. First convert from grams to moles. Then using the coefficients, there's 2 moles of CO2 produced for every 1 mole of maleic acid. So that's my conversion factor. I will stop at moles of CO2, and I'm showing you my unrounded answer just to kind of compare these two values. So that's my number of moles of CO2 coming from maleic acid. Now I'm going to repeat that process starting with the other reactant. So 3.217 grams of sodium bicarbonate. So first grams to moles, and based on the coefficients, there's 2 moles of CO2 produced for every 2 moles of sodium bicarbonate. Now, when I do that calculation, let's see if that compares with 0.03678. Looks like that number is larger. So I'm going to focus my attention on the smaller amount of CO2. So I have now identified the limiting reactant as the one that produces the smaller amount of product. So maleic acid in trial 3 is the limiting reactant because it leads to a smaller amount of CO2 in these stoichiometry calculations. Now, the next part of this question was to determine the theoretical yield of carbon dioxide in grams, which means instead of stopping at moles of CO2, I will stop at grams of CO2. So I'm going to use the information from the periodic table to calculate the molar mass of carbon dioxide. And it turns out that's 44.01 grams of CO2 for every 1 mole. So when I run these calculations, starting with grams, dividing by molar mass times 2 times 44.01, on my calculator I get 1.619 grams of CO2. And when I repeat that process for the sodium bicarbonate, I'm expecting I'm going to get a larger number. And sure enough, when I convert from grams to moles, use the coefficients, and then multiply by the molar mass of CO2, I get 1.685 grams of CO2. So I'm focusing my attention on the smaller amount of product coming from the limiting reactant. Again, maleic acid is the limiting reactant in trial 3 because it leads to a smaller amount of CO2. So what's my theoretical yield of carbon dioxide in grams? It's 1.619 grams of CO2. But if you look at the data table, the mass of CO2 produced in trial 3 is 1.376 grams. So the actual yield is what was obtained from the laboratory experiment. The theoretical yield is what was calculated from the stoichiometry information using mass, molar mass coefficients. So what do I do with the actual yield and the theoretical yield? Well, it looks like I have to calculate the percent yield of CO2. So the percent yield of CO2, that's going to be the actual yield from the data table, so 1.376 grams, divided by my calculated value for the theoretical yield, which is 1.619 grams. And when I do that math, and then times 100, I get 85% yield. So to summarize the answers to part B of this question, maleic acid is the limiting reactant because it leads to the smaller amount of CO2 in my stoichiometry calculations. 1.619 grams of CO2 is the theoretical yield, which comes from the limiting reactant. And then the percent yield is actual over theoretical times 100, and that's 85% yield. And then just a note about the 2024 AP Chemistry exam. I have put links in the video description area to the 2024 AP Chemistry exam, including the scoring guidelines and the chief reader report. All right, so we are done with question 3. Now let's take a look at question 4, which is a multiple choice question. Now, as you examine question 4, you can tell that we are still talking about limiting reactant and theoretical yield. So the question says, in a certain experiment, 14 moles of C5H8O reacts with 78 moles of O2 according to the equation above until one of the reactants is completely consumed. Which of the following identifies the limiting reactant and the theoretical yield of water in this experiment? So our strategy will be to convert each number of moles of reactant into moles of H2O. And the reactant that produces the smaller amount of water in our stoichiometry calculations, that will determine the limiting reactant. And we don't need to worry about going from grams to moles because we are already given moles. So this will be a one-step conversion, moles of reactant into moles of product. I'll start with the 14 moles of C5H8O. And because I'm focusing on water as the product, the coefficients will be 8 for water and 2 for the reactant C5H8O. So you can see I'm putting 8 moles of water on the top and 2 moles of C5H8O on the bottom. And so now with my conversion factor in place, it would be 14 times 8 divided by 2. Now I get 56 moles of water, which is listed as the theoretical yield in choices B and D, but I'm not done yet. I have to convert the other amount of reactant into water and see which one produces the smaller amount of product. So now I'm going to repeat that calculation, but this time starting with 78 moles of O2. And now my coefficients are 8 for water and 13 for O2. So there are 8 moles of water produced for every 13 moles of O2 that is consumed. So 78 times 8 divided by 13, and I get 48 moles of water, which is the correct answer to either choice A or C, but the limiting reactant is going to be O2. So why is the limiting reactant O2? Because it leads to the smaller amount of water. And 48 moles of water is my theoretical yield coming from the limiting reactant. So the correct answer to question 4 is choice C. The limiting reactant is O2, and 48 moles of water is my theoretical yield. Now let's take a look at question 5, which is a free response question. In question 5, it says, a student is given a pure sample of a metal carbonate salt with the generic formula M2CO3. Now, the identity of the metal carbonate salt is unknown to the student, but it is one of the 4 substances listed in the table below. So the identity of the metal carbonate salt is either lithium carbonate, sodium carbonate, potassium carbonate, or rubidium carbonate. And here comes the experiment. The student dissolves 5.00 grams of the metal carbonate salt into water, forming a solution with a total volume of 50.00 milliliters. Now, this solution is completely transferred to a beaker, and an excess amount of barium nitrate is added to the beaker, and the reaction represented by the following equation occurs. So we're looking at a precipitation reaction. So the metal carbonate salt is now dissolved in water, so it's aqueous. It was reacted with an excess amount of barium nitrate, and you can see BaCO3 solid. That is the precipitate that is formed in this reaction. Now, a precipitate can be filtered and dried and weighed, and that's what happens in this experiment. So the barium carbonate solid is filtered, dried, and weighed, and the data are recorded in the following table. Now, in this data table, I see 2 masses. I see the mass of the metal carbonate salt dissolved in water, which is 5.00 grams, and then I also see the mass of the barium carbonate precipitate, which is 7.14 grams. So part A of this question says, On the basis of the experimental data shown in the table above, calculate the molar mass of the metal carbonate salt M2CO3 used by the student in this experiment. Well, I see 5 grams, but unfortunately we don't know the identity of the metal carbonate salt. So while I know the grams, I can't convert from grams to moles because I don't know the chemical formula of the metal carbonate salt. But let's take a look at the other mass that we're given. We are given 7.14 grams of barium carbonate. Now, we know the mass of the barium carbonate and we also know its chemical formula. So this looks like a good place to start our calculations. Let's convert from grams to moles. So 7.14 grams of BaCO3, and then using the information from the periodic table to calculate the molar mass, that would be 1 mole of BaCO3 for every 197.34 grams. Now, if I stop right now, that would be moles of barium carbonate. But take a look at the details of the balanced chemical equation. For every 1 mole of this metal carbonate salt that reacted in this experiment, we produce 1 mole of solid barium carbonate precipitate. I will add that to my calculations. And now if I do this math of 7.14 divided by 197.34, I don't just get moles, I get moles of a chemical that I don't know the identity of, at least not yet. So I have moles of M2CO3, and that works out to be 0.03618. So how does this help me answer part A of this question? Well, if you have grams and you have moles for the same substance, then you can connect grams and moles. So molar mass is grams per mole. That means that grams divided by moles will give us what we're looking for. So 5.00 grams of this mystery substance, the metal carbonate salt, divided by 0.03618 moles of that same substance. If I do that math, 5 divided by 0.03618, I get approximately 138.2. So 138 grams per mole, that is the answer to part A. And now that I know that the molar mass of the metal carbonate salt that was used in the experiment is 138 grams per mole, I can now move on to answer part B of this question. So part B says, based on your answer to part A, which of the following substances is most likely to represent the identity of the metal carbonate salt used by the student in this experiment? Answer by drawing a circle around one of the choices shown below. So I'm looking for 138 grams per mole. So is it lithium carbonate? No, that's around 74 grams per mole. Is it sodium carbonate? No, that's around 106 grams per mole. Is it potassium carbonate? Yes. Potassium carbonate has a molar mass of approximately 138 grams per mole. And it's not rubidium carbonate because rubidium carbonate has a molar mass of approximately 231 grams per mole. So because the answer to part A was 138 grams per mole, that makes potassium carbonate the most likely identity of the metal carbonate salt used by the student in this experiment. Now, one more part of this question, this is part C. It says, calculate the molar concentration of the carbonate ions in the 50 milliliter sample of solution that was present in the beaker before the barium nitrate was added. So we have 5 grams of a metal carbonate salt, but we now know the identity of that. So let's convert from grams to moles because we know it's potassium carbonate. And then once we have moles, then we can do moles divided by liters. So concentration or molarity, that would be moles of solute per liter of solution. So we'll start with 5 grams of the metal carbonate salt. This is not a mystery anymore. This is potassium carbonate. So 5 grams of potassium carbonate. There's my conversion factor to go from grams to moles. And there's 1 mole of carbonate ions present for every 1 mole of potassium carbonate. So if I do 5 divided by 138.21, I get the number of moles of carbonate ions. So 0.03618, that's the number of moles of carbonate ions. And molarity is moles per liter. So if I take that number of moles of carbonate ions and divide by the volume in liters, and 50 milliliters would be 0.0500 liters. Again, you're dividing by 1,000. When you go from milliliters to liters, you divide by 1,000. I take 0.03618 moles of carbonate ions divided by 0.0500 liters of solution. And when I get my answer for moles per liter, it's 0.724 moles per liter. That is the concentration of the carbonate ions in the 50 milliliter sample of solution that was present in the beaker before the barium nitrate was added. Now, you can write 0.724 with units of moles per liter, and you can also use a capital M to abbreviate molarity. So there is your answer to part C of this question, and now it is time to move on to the review for topic 4.6, Introduction to Titration. Here is an essential knowledge statement from the AP Chemistry course and exam description. Titrations may be used to determine the concentration of an analyte in solution. The titrant has a known concentration of a species that reacts specifically and quantitatively with the analyte. The equivalence point of the titration occurs when the analyte is totally consumed by the reacting species in the titrant. The equivalence point is often indicated by a change in a property such as color that occurs when the equivalence point is reached. And this observable event is called the endpoint of the titration. Now let's move on to the practice for topic 4.6. This is question 6. In question 6, we are given a balanced chemical equation and a description of a titration experiment. It says, in a titration experiment, a student added 25.0 milliliters of an acidified iron 2+ solution to an Erlenmeyer flask. Then the student titrated the iron 2+ solution in the flask with a solution of potassium permanganate, KMNO4, which has a dark purple color, and the balanced chemical equation for the reaction that occurred during the titration is shown above. Then it says that the student used a 50 milliliter burette to add the potassium permanganate solution to the iron 2+ solution until a faint lavender color was observed in the flask, an indication that the end point of the titration has been reached. And the initial and the final volume readings of the solution in the burette are shown below. So here we can see the initial reading on the burette on the left and the final burette reading on the right. Let's go ahead and zoom in even further. Now, with a burette, you normally read a burette from top to bottom. And that means that the initial volume reading is somewhere between 5 milliliters and 6 milliliters. It's also important to note the precision of the burette. So every line on the burette represents 0.1 milliliters. So we read the volume on the burette to the nearest 0.01 milliliters. So your volume reading should have 2 decimal places. Now it looks like this volume reading is 5.5, and I think it's exactly on the line so that the bottom of the meniscus seems like it's exactly at 5.5. But remember, 2 decimal places, so I'm going to record that volume reading as 5.50 milliliters. Now, moving on to the final burette reading, I would say it's, again, from top to bottom, somewhere between 37 and 38 milliliters. Now, I would say it's somewhere between 37.7 and 37.8. Again, I'm going to read my volume to 2 decimal places, so I'm going to say 37.79. Again, I'm looking at the bottom of the meniscus. It seems like it's just above 37.8, so 37.79 seems good to me. Now, let's move on to our first part of this question. As you can see, the student wrote down 5.5 milliliters for their burette reading, and Part A says to identify the error associated with the initial burette measurement recorded by the student. And so the answer to Part A is what I talked about, and that is the student did not record the volume with 2 decimal places according to the precision of the burette. Now, in Part B, we have a different error. So read the burette to 2 decimal places. We've taken care of Part A. Let's take a look at Part B. I wrote down 37.79 for my volume reading, but the student wrote down 38.21. So another common mistake that can be made by AP Chemistry students is to read the burette incorrectly. So the student incorrectly read the volume from the bottom up. That's why they said 38.21. But the correct volume reading should be from the top down, so 37.79. And now in Part C, it says write down the correct measurements for the initial and final burette readings. So it's going to be 5.50, 37.79, and now the difference between the final and the initial, this will tell us how much of that potassium permanganate solution was added from the burette. And so that difference is 32.29. So Part C, we've written down the correct measurements for the initial and the final burette readings, and we used these values to determine the volume of the potassium permanganate solution that was added during the titration. Now, if you have a volume and you have a concentration, you can calculate the number of moles. So let's see, what is the concentration of the potassium permanganate solution? So Part D says, given that the concentration of the potassium permanganate solution used in the titration was 0.0236 moles per liter, calculate the number of moles of permanganate ions that completely reacted with the iron 2+ ions in this experiment. So I'll start with the volume from Part C, so 32.29 milliliters. I will first convert from milliliters to liters by dividing by 1,000, and then I will use 0.0236 moles of potassium permanganate for every 1 liter. That's simply the definition of molarity, and I'm using it as a conversion factor. So when you do volume in liters times the molarity, which is moles per liter, you can calculate the number of moles. And potassium permanganate has 1 mole of permanganate ions for every 1 mole of potassium permanganate. So 32.29 divided by 1,000 times 0.0236, that gives me a 0.000762044. I haven't rounded off this answer. I'm going to use 4 significant figures based on 32.29, and I think I will write this number in scientific notation. So it's going to be 7.620 times 10 to the negative 4. That is my number of moles of permanganate ions. So that is my answer to Part D. Remember, this is a titration in which there was a reaction with iron 2+. Let's go ahead and use the stoichiometry to answer Part E of this question. So calculate the molar concentration of the iron 2+ ions in the 25.0 milliliter sample of solution that was present in the flask at the beginning of this titration experiment. So let's take a look at our balanced chemical equation, because we have to go from moles of permanganate ions to moles of iron 2+ ions. So with my balanced chemical equation, that would be a 5-to-1 ratio. There's 5 moles of iron 2+ in the balanced equation for every 1 mole of permanganate. So I'm going to take my answer to Part D, which is 7.620 times 10 to the negative 4 moles of permanganate ions, times 5 moles of iron 2+ for every 1 mole of permanganate. Now, I've got a number on my calculator, and it's 3.810 times 10 to the negative 3, but my units are moles. Remember that moles and molarity are not the same thing. So this is moles, but this is not molarity. Moles divided by liters is molarity. So this question said, calculate the molar concentration in the 25.0 milliliter sample, and 25.0 milliliters, when you divide by 1,000, that is 0.0250 for the volume of the solution. And I've got moles of iron divided by the volume of the solution, and I get 0.152 moles per liter. So the answer to part D was 7.62 times 10 to the negative 4 moles of permanganate ions. And then using the stoichiometry, I converted from moles of permanganate to moles of iron. And then I took the moles of iron and I divided by the volume of the solution. So my answer to part E is 0.152 moles per liter. That's my concentration of the iron ions. All right, well, that's the end of this question. So now let's take a look at question 7. Question 7 is an example of an acid-base titration experiment. We are given a balanced chemical equation, and it says a 10.0 milliliter solution of propanoic acid, which has the formula HC3H5O2, is titrated with 0.20 molar sodium hydroxide, NaOH. Now, the reaction represented by the equation shown above occurs during the titration, and the following titration curve is produced. Now, the most important feature of this titration curve is what happens when all of the propanoic acid reacts completely with the sodium hydroxide. So what you're looking for is that rapid increase in pH, and that seems to occur around 14 milliliters on the x-axis in this diagram. So what I'd like to do is I'm going to summarize what we know about the volume and the molarity for both the acid solution and the base solution in this experiment. So I'll start with the acid. So we know that we have a volume of 10 milliliters for the propanoic acid, but at this point we don't know the exact concentration of the propanoic acid. So that's what we're trying to find. Now, for the base, we know that we can read from the titration curve where the equivalence point occurs, and that is at 14 milliliters. We also know that for the sodium hydroxide, it has a concentration of 0.20 moles per liter. So what we're trying to find is the concentration of the propanoic acid. Now what I'm going to do is show you a diagram with a burette and a flask, just to show you what's in the burette and what's in the flask during this experiment. So what's in the burette is the sodium hydroxide solution. We know the concentration of the sodium hydroxide is 0.20 moles per liter, and we know from the titration curve diagram that 14 milliliters of sodium hydroxide is added from the burette to reach the equivalence point of the titration. Now in the flask is the propanoic acid, so we know its volume is 10.0 milliliters, but at this point we don't yet know the concentration of the propanoic acid. So since I have a balanced chemical equation and the fact that there is the acid HC3H5O2 and there is the base sodium hydroxide, I can see that all the coefficients are 1. So there is a 1-to-1 mole ratio between the acid and the base. Since I know both the volume and the molarity of the sodium hydroxide, then that's where I'm going to start my calculations. So I'll begin with volume. So volume is 14 milliliters. I will convert from milliliters to liters by dividing by 1,000. And then I will use the molarity, which is 0.20 moles of sodium hydroxide per liter. So remember that volume in liters times the molarity gives you the number of moles. Now at this point, I have 14 divided by 1,000 times 0.2. On my calculator, I get 0.0028 moles. That's moles of sodium hydroxide. But remember, there is a 1-to-1 mole ratio between the acid and the base, so not only is 0.0028 the number of moles of sodium hydroxide, based on the stoichiometry, it is also the number of moles of propanoic acid. Now, why am I dividing by 0.01? It's because volume in liters, 10 milliliters divided by 1,000 is 0.0100. And why am I doing moles over liters? Because that will give me concentration. So 0.0028 moles of propanoic acid divided by its volume in liters, there is my answer for the concentration of propanoic acid. So 0.28 moles per liter is the calculated value for the concentration of the propanoic acid for this titration experiment. Now, in part A, it says the volume of the propanoic acid solution that was titrated was 10 milliliters. But notice that I'm not starting with 10 milliliters. I'm starting with the volume of the sodium hydroxide. I can't begin with 10 milliliters because I don't know the concentration of the propanoic acid. So I'll just repeat that calculation that I showed you on the previous slide. So I'm going from 14 milliliters into liters. I'm using the sodium hydroxide concentration, so 14 milliliters of 0.2 molar sodium hydroxide. There's that 1-to-1 mole ratio between the sodium hydroxide and the propanoic acid. There's that 0.0028 moles that I had mentioned, divided by the volume in liters. So 0.0028 moles of propanoic acid divided by 0.010 liters of solution for the propanoic acid, and there's my answer to part A. So the concentration of the propanoic acid is 0.28 moles per liter. Now, there is a part B of this question where we have to draw a titration curve based on a change in the experimental conditions. So it says the student performs a second trial with another 10 milliliters solution that has the same concentration of propanoic acid as the solution used in trial 1. But the student uses a solution of not 0.2 but 0.10 molar sodium hydroxide. So they're reducing the concentration of the sodium hydroxide in the burette from 0.2 molar to 0.1 molar. And on the graph above, we have to draw the titration curve that would be expected for trial 2. So 14 milliliters was the location of the equivalence point for trial 1. What would happen if you reduce the concentration of sodium hydroxide from 0.20 molar to 0.10 molar? Well, if you reduce the concentration, then you're going to double the volume. Because we're going to have half the number of moles per liter, then we need twice the volume. So to get the same number of moles, if we reduce the concentration by half, we have to increase the volume. That means that the volume of sodium hydroxide required to reach the equivalence point in trial 2 will increase from 14 milliliters to 28 milliliters. So I will start my curve at the exact same initial pH because that would be the pH of the acid that I started with, and that's not changing. But I have to move this vertical portion of the titration curve from 14 milliliters to 28 milliliters. So what you can see in red on this slide is my drawing of the titration curve for trial 2. So it follows the same general shape, but I have shifted from 14 milliliters to 28 milliliters for the location of that rapid change in pH. All right, well, that is the answer to part B of this question. Now let's take a look at question 8, which is a multiple choice question. Now, there are some similarities and differences between question 7 and question 8. In question 7 and question 8, we're involving an acid-base titration experiment, so that's similar. We have a titration curve, so that's similar. But the difference between question 7 and question 8 is the following. In question 7, we knew the concentration of the sodium hydroxide in the burette, but we didn't know the concentration of the propanoic acid in the flask. But here in question 8, it's sort of reversed. We are given that this is hydrochloric acid reacting with sodium hydroxide, and so the difference is that now we don't know the concentration of the sodium hydroxide in the burette, but we do know the concentration of the hydrochloric acid in the flask. So here's what it says in question 8. A 50 milliliter sample of a 0.100 molar solution of hydrochloric acid, and that is titrated with a sodium hydroxide solution of unknown concentration. So based on the titration curve shown at the right, what is the molar concentration of the sodium hydroxide solution? So I'm going to draw a diagram like I did in question 7, and let's determine what's in the burette and what's in the flask. So what's in the burette is sodium hydroxide, but we don't know the concentration of the sodium hydroxide. How much volume was added comes from reading that rapid rise in pH. So along the x-axis, the location of the equivalence point looks like that would be at 10 milliliters of sodium hydroxide was added, and we can read that from the titration curve diagram. Now with the flask, that is 50 milliliters of hydrochloric acid, and we do know that the concentration of hydrochloric acid is 0.100 moles per liter. Now, they didn't give us a balanced chemical equation in this question, but we can write one. So hydrochloric acid, HCl, reacts with sodium hydroxide, NaOH, and it produces both water and sodium chloride. And just like we saw in question 7, we have another example of an acid reacting with a base with a 1-to-1 mole ratio between the acid and the base. I can't start with the sodium hydroxide because I don't know its concentration, so I will start with the hydrochloric acid. We know both the volume and the molarity, so we can calculate the number of moles. So it's going to be 50 milliliters, and I will divide by 1,000 to go from milliliters to liters. It's 0.100 moles of hydrochloric acid for every 1 liter. So if I do 50 divided by 1,000 times 0.1, I get 0.005, and that's my number of moles of HCl. But remember, there is a 1-to-1 mole ratio between the acid and the base. That means that 0.005 is also the number of moles of sodium hydroxide. And that was 10 milliliters of sodium hydroxide added from the burette, as we read from the titration curve diagram. So 10 milliliters is equal to 0.01 liters when you divide by 1,000. So if I do moles over liters, 0.005 moles divided by 0.01 liters, I get the concentration of the sodium hydroxide in units of moles per liter. So that is the correct answer to question 8. I will show you that one more time. So I'm starting with the volume of the HCl, which is 50 milliliters. Divide by 1,000 to go from milliliters to liters, multiply by the molarity to go from liters to moles, so that's 0.100 moles of HCl per liter. Then, based on the stoichiometry and the 1-to-1 mole ratio between HCl and NaOH, and then recognizing that that number of moles of sodium hydroxide would be dissolved in a total volume based on the rapid change in pH, that's 10 milliliters. So that's 10 milliliters of the sodium hydroxide solution that was used to reach the equivalence point. I'm going to take moles over liters. So 0.005 moles of sodium hydroxide divided by 0.010 liter of solution. That gives me my concentration of sodium hydroxide in units of moles per liter. So it's 0.500 moles per liter, and so the correct answer to question 8 is choice C. So now you've seen 2 examples of acid-base titrations in question 7 and question 8. Let's go ahead and take a look at question 9. It looks like it's another example of an acid-base titration, but we have a different problem to solve. This time in question 9, we're looking at determining the molar mass of an acidic substance. All right, let's go ahead and consider the details of question 9. It says, a chemist performed a titration experiment in order to determine the molar mass of an acidic substance, and the chemical formula HX represents this acid. We just don't know the exact chemical formula, so we have to figure out the molar mass. That's what we're doing in question 9. Now, the chemist dissolved a sample of solid HX in water and added a few drops of an acid-base indicator to the solution to ensure visual detection of the endpoint. The chemist titrated the HX solution with potassium hydroxide, or KOH, so that's the base in this experiment. And the chemical equation for the reaction that occurred during the titration is shown above. Data from the experiment is shown in the table below. Now, we have mass of HX is 0.100 grams, but we can't convert that from grams to moles because we don't know the molar mass of HX. We have an initial burette reading, which is 3 milliliters. We have a final burette reading of 8.56 milliliters. So that difference, 8.56 minus 3, that gives us the volume of the potassium hydroxide solution that was used in this titration experiment. And we know the volume, and we also know the molarity. So remember that when you know the volume and the molarity, you can calculate the number of moles. So I'll start with 5.56 milliliters. I will divide by 1,000 to go from milliliters to liters. And the concentration of the potassium hydroxide, that's the titrant in this experiment, is 0.100 moles of potassium hydroxide per liter. Now, if I stopped right now, I would have moles of potassium hydroxide. But look at the information in the balanced equation. Again, another example of a 1-to-1 mole ratio. So there's 1 mole of HX for every 1 mole of KOH. So now if I stop and I do 5.56 divided by 1,000 and then times 0.1, what I'm going to get is a number on my calculator, which is moles of HX. So I will write that down. That's 5.56 times 10 to the negative 4 moles of HX. Now the question says we have to calculate the molar mass of HX. So what are the units of molar mass? Well, the units of molar mass are grams per mole, which means if we could take the grams of HX, which we know, and divide by the number of moles of HX, which we also know, we've just calculated that, then we can determine the answer to question 9. So grams divided by moles would be molar mass. The grams are 0.100. The moles that we just calculated is 5.56 times 10 to the negative 4. So if I pick up my calculator and do 0.1 divided by 5.56 times 10 to the negative 4, then what I get should be the molar mass of HX. And I get 180 grams per mole when I do that calculation. So that means that the correct answer to question 9 is choice D. So we took the volume of the potassium hydroxide and the molarity. We calculated the number of moles of potassium hydroxide, and based on that 1-to-1 ratio in the balanced equation, we also got the moles of the acid. Grams divided by moles gives us the molar mass. All right, well, that's the answer to question 9. There's only one more question in this packet. It's also another example of an acid-base reaction, but what I like about question 10 is that it's not a 1-to-1 mole ratio between the acid and the base, and I think it's important that every so often you realize that not every acid-base reaction will be 1-to-1 in terms of the mole ratio. All right, let's go ahead and take a look at question 10. All right, so question 10 starts by telling us information about an antacid tablet. It says, an antacid tablet containing solid magnesium hydroxide, that's Mg and then parentheses OH2, that solid magnesium hydroxide, which by the way is going to be present in the flask, is titrated with a solution of nitric acid, which has the chemical formula HNO3. So if the magnesium hydroxide is in the flask, that means that the nitric acid is in the burette. Now the end point is determined by using an indicator, and we are given the initial and final burette readings from the titration, which are listed in the table below. So again, the burette readings are for the solution of nitric acid. The magnesium hydroxide is a solid that is in the flask. Now part A of this question says write a balanced chemical equation for the acid-base reaction that occurs between solid magnesium hydroxide and aqueous nitric acid during the titration. The products of the reaction are water and aqueous magnesium nitrate. Now, will this be a 1-to-1 mole ratio between the acid and the base? No. And that's why it's important to realize that not every acid-base chemical reaction that you see on the AP Chemistry exam will be a 1-to-1 mole ratio. This one happens to be a 2-to-1 mole ratio between the acid and the base. Let's take a look at our formulas. So we have magnesium hydroxide, reacting with nitric acid, and the products are water, H2O, and magnesium nitrate, Mg, and then parentheses NO3 Now this equation is not balanced until we put a 2 in front of the nitric acid to balance the nitrate ions on the right. And now we have 4 hydrogen atoms on the left, so we need to put a 2 in front of the H2O to balance the 4 hydrogen atoms. All right, well now this equation is balanced, but notice it is 1 mole of magnesium hydroxide for every 2 moles of nitric acid. All right, let's move on to part B, and I'm sure we'll need to use those coefficients in our stoichiometry calculations. Remember that the nitric acid is in the burette, so it says, given that the concentration of nitric acid used in the titration was 0.200 moles per liter, calculate the number of moles of nitric acid that completely reacted with the magnesium hydroxide in this experiment. So I subtracted the final and initial values, so 20.76 minus 2.75, that gives me a volume of 18.01 milliliters of the nitric acid, and that is 0.200 moles of nitric acid per liter. Now remember, when you know the volume and the molarity, you can calculate the number of moles. So there's my volume, which is in units of milliliters. So I will divide by 1,000 to go from milliliters to liters, and then I will multiply by the molarity as a conversion factor, so 0.200 moles of nitric acid for every 1 liter. Now I will finish off with this problem. It's 0.003602 on my calculator when I did 18.01 divided by 1,000 times 0.2. But remember, there's going to be a connection with the stoichiometry to the next part. So the last part of this question, now that we have our answer to part B, says calculate the mass in grams of the magnesium hydroxide that was present in the antacid tablet. Can we assume it's a 1-to-1 mole ratio between the acid and the base? Obviously not. We've already answered that in part A. So I'll write down my answer to part B, 0.003602, and that's moles of nitric acid. Now, will this be a multiply by 2 or divide by 2? If you're not sure, you should definitely use your units to make a conversion factor. So I'm going to put moles of HNO3 on the bottom, and I'm going to put moles of magnesium hydroxide on the top. So that would be, based on the stoichiometry, there's 2 moles of nitric acid for every 1 mole of magnesium hydroxide. So that's going to be 1/2. So we're going to divide by 2. And at this point, if I stopped right now, I would have moles of magnesium hydroxide. Now, they want the mass in grams, so my next conversion factor simply involves the molar mass of magnesium hydroxide. So I calculated the molar mass of magnesium hydroxide from the periodic table, and that worked out to be 58.316 grams of magnesium hydroxide per mole. So when I pick up my calculator, this is the last part of this question, it's 0.003602 divided by 2 times 58.316, and then my answer will be grams of magnesium hydroxide. And so when I did that math, I got 0.1050 grams of magnesium hydroxide. So now we have come to the end of this question. So now it is time to move on to the part of the lesson where I give you advice to help you avoid common mistakes. So the first thing that I will mention is that if you are interested in additional practice problems for topics 4.5 and 4.6, you can review the information in my video, and that's linked in the video description area. My next piece of advice is what I normally say. It's very important to read the question carefully and make sure you are answering the question that is being asked. Now, because we're talking about calculations, if a calculation involves multiple steps, don't round off your numerical values to the intermediate steps, because that can create a problem where your answer doesn't quite match the intended answer. So wait until the end. And then when you're finished with all of the steps of your calculation, round off your final answer to the proper number of significant figures. Now, with respect to significant figures, the molar mass comes from the information on the periodic table. The molar mass should not be the limiting factor in significant figures, so use as many digits as possible when working with the information from the periodic table in your calculation of the molar mass of a substance. Now, be careful to avoid the following common mistakes with stoichiometry calculations, and they include an incorrect molar mass value, incorrect unit conversions when converting from milliliters to liters or vice versa, incorrect conversions of units when converting from grams to moles or vice versa. Don't assume that the mole ratio is 1:1, so pay attention to the coefficients from the balanced chemical equation. Some students will use the correct coefficients, but they flip them upside down, so just make sure that you're focusing on the units about whether the moles of one chemical goes on the bottom or the top of your conversion factor. And then some students don't show any units in the setup for their calculations, and this can increase the risk of making calculation errors or algebra errors. Some students don't show any work. You must show your work on the AP Chemistry exam to receive credit for your answer. Now, if the question gives you a balanced chemical equation for a certain reaction or process, well, then be aware that the coefficients in the balanced chemical equation, they represent the mole ratios, or the relative number of moles of each substance involved in that reaction or process. If the question discusses a chemical reaction, like we saw with combustion or some acid-base, and you are not given a balanced chemical equation in the question, it is a good idea to write the balanced equation for the reaction. Now, if you're given a diagram or a data table related to a laboratory experiment, pay attention to the units. The units can be your guide as you set up your calculations and conversion factors. Remember that although they are similar in terms of what we're talking about, with stoichiometry, moles, molarity, and molar mass are not the same thing. So just watch out for that mistake. And if you are given volume, when the volume of a solution is in liters is multiplied by the molarity, then this will give you the calculated value for the number of moles of the solute in that solution. It's important to do laboratory experiments, especially those involving stoichiometry calculations or titrations, because that laboratory experience can give you experience with the types of laboratory situations that involve topics 4.5 and 4.6. Another good strategy for topic 4.3, particle representations of chemical reactions. This can be a good way to illustrate the limiting reactant and the excess reactant. Now, the limiting reactant is described as follows. It is the reactant that is completely consumed in the reaction. It is the reactant that leads to a smaller amount of product in your stoichiometry calculations. It is the reactant that determines the maximum amount of product that can be formed, and which is known as the theoretical yield. If the amount of the limiting reactant is increased, then the amount of product formed in the reaction should also increase. The excess reactant is described as follows. Some of this reactant will remain left over after the limiting reactant has been completely consumed in the reaction. The excess reactant cannot be used to determine the theoretical yield. And if the amount of the excess reactant is increased, then the amount of the product formed in the reaction should remain the same. Percent yield is not the same as percent error. The experimental yield, or the actual yield, is what is obtained in the laboratory, and the theoretical yield comes from the stoichiometry calculations involving the limiting reactant. Data from a titration experiment frequently involves two different volumes and two different concentrations of solution, so pay attention and make sure that you use the correct volume with the correct concentration. That's a very common thing we see on the AP Chemistry exam. Students will switch the volume of the acid with the concentration of the base, or vice versa. Some titration experiments involve reactants with mole ratios that are not 1:1, so therefore it's not a good idea to use the so-called dilution equation, or M times V equals M times V, in a titration calculation unless you know for sure that the stoichiometry of the reactants involves a 1-to-1 mole ratio. So I hesitate to teach you that shortcut of M times V equals M times V. I would rather you do volume times molarity equals moles, and then look at the coefficients to go from moles of one chemical to moles of another. With respect to titration curves, be familiar with the general features of a titration curve for an acid-base reaction, and I can tell you that in a future episode of AP Chemistry Review and Practice, I will have more to say about titration curves. So that is covered in topic 8.5 in the AP Chemistry curriculum. A burette is a precise piece of glassware that is used in a titration. When you are preparing to do a titration, after a burette has been cleaned and rinsed with water, the burette should be rinsed with a small amount of the solution that will be used to fill the burette. This rinsing solution is used to coat the interior walls of the burette with the solution that will be used to fill the burette. After coating the inside of the burette with the rinsing solution, this solution should be drained from the burette, and now that it's been rinsed with that solution, then the burette can be filled with that same solution. And the rinsing procedure is necessary because otherwise there could be droplets of water inside the burette. And so that rinsing procedure is necessary because it minimizes the interference of any water droplets that are inside the burette, because water would dilute and lower the concentration of the titrant solution. Other important features as far as volume readings of a burette: the volume of a burette is normally reported with 2 decimal places. We normally read the burette from top to bottom, and if there is a meniscus, use the bottom of the meniscus to make your volume reading. Subtract the initial volume reading from the final volume reading to calculate the volume of the titrant solution that was added to the flask from the burette. So we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 4.7 to 4.9. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry's CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.